Hi, I'm Hengfeng Wei from Nanjing University. I'm going to talk about efficient black box checking on snapshot isolation in databases. This is a joint work of researchers from Nanjing University, ETH Zurich, and Tencent. A transaction is a group of operations that are executed atomically. The isolation levels specify how concurrent transactions are isolated from each other. The serializability isolation level requires that all transactions appear to be executed in some total order. However, implementing serializability is too expensive. Snapshot isolation is a weak isolation level. It allows each transaction to read data from a snapshot as of the time the transaction started. In this example, we have two transactions, which concurrently read the two accounts, compute their sum, and withdraw money if possible. On the snapshot isolation, these two concurrent transactions are allowed to read from the initial snapshot of these two accounts and withdraw money successfully. As a result, the sum of these two accounts becomes negative. This is a write skew anomaly which is allowed by snapshot isolation. On the other hand, concurrent transactions cannot write to the same key. In this example, we have two transactions concurrently reading from the shared account and adding some money to it. On the snapshot isolation, one of these two concurrent transactions must be aborted. This prevents the lost update anomaly. Many database systems implement snapshot isolation. However, they may fail to provide snapshot isolation correctly. The SI checking problem is the decision problem of determining whether a history of a database system satisfies snapshot isolation. Here, a history is a pair consists of a set T of transactions and the session order between these transactions. A good SR checker should be sound, meaning that if the check says no, then the history does not satisfy snapshot isolation. Complete. If the check says yes, then the history satisfies snapshot isolation. Efficient. The check should scale up to large workloads. And informative. The check should provide understandable counterexamples if it finds violations. DeepCover is a checker for snapshot isolation. However, it's not practically efficient and is not informative. Cobra is a checker for serializability. However, the SI checking problem is harder. L is a checker for various isolation levels. It works perfectly on traceable and recoverable histories, but it may be incomplete on the key value data type. The SI checking based on the alias of notions relies on the start and commit timestamps of transactions. The SI checking based on the Ghostman notions may miss snapshot isolation violations. So in this work, we propose a PolySci checker which is sound, complete, efficient, and informative. PolySci encodes the checking problem as a set formula. The soundness and completeness of this step relies on a novel polygraph-based characterization of snapshot isolation. Then it feeds the formula into a norm set solver, which is optimized for graph problems. Also for efficiency, PolySci will prune the constraints on polygraph before encoding. Finally, if the norm set solver finds a violation, PolySci will extract counterexamples from the onset call. The theory behind PolySci is the polygraph-based characterization of snapshot isolation. But before this, we first review the dependency graph-based characterization of snapshot oscillation. The theorem says that a history satisfies snapshot oscillation if and only if there exists a dependency graph for it that contains only cycles with at least 2 adjacent RW edges. What does this mean? Let's consider an example. We have 4 transactions. The write-read dependency captures the read-from relation between these transactions. The write-write dependency captures the version order on account. Because TA reads from T0, and T0 is overwritten by TB, we can infer that TA is before TB. We call this dependency the read-write dependency. Similarly, TB is before TA in terms of RW. Then, the dependency graph contains a cycle, but this cycle is allowed by snapshot oscillation because it contains 2 adjacent RW edges. Now, we still don't know the WW dependency between TA and TB. There are 2 possible cases. First, suppose that TA is before TB. Then the dependency graph contains an undesigned cycle for SI. On the other hand, if TB is before TA, then the resulting dependent graph also contains an undesigned cycle for SR. In summary, we have considered both cases, and each case leads to an undesigned cycle for SR. Therefore, this history does not satisfy SR. This is an equivalent form of the previous theorem. It checks the induced graph G of a dependence graph is acyclic. To get the induced graph of a dependence graph, we first compose the SOWR or WW edges with the RW edges. For example, the dependence graph will have TA is before TB in terms of WW, and TB is before TA in terms of RW. And by composing these 2 edges, we can add an edge in the reduced graph from TA to itself. Then we delete all the RW edges to get the final induced graph. Now the problem is how to capture all the possible dependency graphs. To do this, we introduce polygraph. Intuitively, a polygraph is a family of dependency graphs. For example, we can merge these 2 possible dependency graphs into a single polygraph. Polygraph uses such either-or constraints to capture the 2 possible cases of WW dependencies between TA and TB. Now we are ready to explain the whole polycy procedure with a running example, including constraint pruning, set encoding, and norm-set solving. There are 6 transactions. We need to determine the WW dependency between T0, T1, and T5 on X, and the WW dependency between T0 and T2 on Y. First, consider T0 and T5. Because T0 is before T5 in the same session, we can infer that the WW dependency from T5 to T0 can be safely pruned due to this cycle. Therefore, the other direction from T0 to T5 becomes known. Similarly, the WW dependency from T1 to TW can be safely pruned due to this cycle. Therefore, the other direction becomes known. Also, the WW dependency between T2 to T0 can be pruned, while this direction becomes known. Now, the WW dependency between T1 and T5 is still uncertain after pruning. For this, we will encode the two possible cases into an either-or constraint in the polygraph. These constraints will be encoded into a Boolean formula. For example, this Boolean formula says that either this case holds, but this case does not hold, or this case holds, but this case does not hold. Finally, we need to encode the induced graph. For example, in this part, we know that T1 is before T3 in terms of WR, and T3 may be before T5 in terms of RW. Then we know that the presence of the edge T1 to T5 in the induced graph depends on the edge T1 to T3 and the edge T3 to T5 in the polygraph. We fit the final set formula into the norm set solver, which is optimized for cycle detection. The norm set solver will find an undesigned cycle for the example. In the experimental evaluation, we answer the following three questions. Can PolySci find snapshot isolation violations in production databases? Can PolySci provide understandable counterexamples for SI violations? And how efficient is PolySci? This tab shows the workload parameters and their default values. We use 6 benchmarks, including Rubis, TPCC, CTwitter, and 3 artificial workloads with different ratios of read and write operations. PolySci is able to reproduce known snapshot isolation violations in a collection of more than 2,000 histories. It's also about to detect new SI violations. We have found 3 violations, 2 of which have been confirmed by the developers. When the norm set solver finds a violation, it will output a cycle, but this cycle may be too simple to understand. So PolySci will restore the missing participant transactions, recover the dependencies between these transactions, and finalize them to get an understandable counterexample. For performance evaluation, besides dbCorp, we also implement Cobra SI, which reduces SI checking to serializability checking to leverage Cobra with or without GPU. The results show that PolySci significantly outperforms the competitors. PolySci consumes less memory. Also, PolySci can scale up to large workloads with 1 million transactions in several hours. We also do some differential analysis. We found that the pruning step is crucial to the efficiency of PolySci. This is because that PolySci can prune a huge number of constraints before encoding. To conclude, we have proposed a snapshot isolation checker called PolySci, which is sound, complete, efficient, and informative. PolySci uses norm set as a black box. As a future work, we are now working on a series solver dedicated to isolation level checking, which is deeply integrated with set solvers. Thank you.